Hello. The first few exercises you've just completed called upon you to use what you've learned in the other exercises on generating Bernoulli random variables. In this exercise, we're going to learn how to compute histograms. You already did this in the previous task, however, when you counted the number of successes and failures you obtained when you generated your Bernoulli random variables. We will thus extend these ideas as we complete this exercise. If you did the previous task correctly, and if you had plotted the two numbers your function outputted, you should have got a result that should look something like the graph shown on the left-hand side of this slide. The bar centered on 0 tells you the fraction of your Bernoulli random variables that were equal to 0, while the bar centered on 1 tells you the fraction of the Bernoulli random variables that were equal to 1. In other words, the heights of these two bars tells you the number of failures and successes in your trials respectively. The Python code that generated this graph is shown on the right-hand side of this slide now. If we focus on only the parts that I've shown here, this code should be very familiar to you by now. All this is doing is generating a sample of 200 Bernoulli random variables, which we have now done many times. Let's now turn to the first new bit of code that we've introduced in this exercise, which I am now re-showing you here. This first line here creates two arrays, both of which have two elements. The first of these arrays, xvals, just contains the numbers 0 and 1, and this ultimately will be used for the x-coordinates of our bars. The second, meanwhile, has both elements set equal to 0 initially. As the loop executes, however, the 0th element is used to count the number of random variables that are equal to 0, while the first element is used to calculate the number of random variables that were equal to 1. Consequently, we have a list, once the loop is finished, that contains the number of failures in its first element and the number of successes in its second element. We can thus plot a bar chart with xvals against yvals and get something like the plot shown on the left-hand side of the slide. The estimate of the probability mass function that you would get if you plotted the data in this way would not be normalized, however. Adding together the heights of all the bars would give you n, the number of data points, rather than 1. To get a normalized graph, we thus divide each element of yv by the number of variables we sampled as shown above. The sum of the heights of the bars is then equal to 1, as is required and as is illustrated here. Hopefully, the code is relatively clear and easy to understand. There is, however, one command within here that you might be worried about, namely the int here. This command turns a real number into an integer. Unfortunately, we need to know some computer science here to understand what's going on. For the computer, 1 is an integer and 1.0 is a real number. And unfortunately, integers and real numbers are represented in different ways within the computer's memory. Python looks after much of the conversions between representations of numbers for you, but in some cases, you have to help Python to interpret what you mean. This is one such occasion where you can have problems because Python tries to use a real number where it needs an integer. If you try to use the real number 1.0 here to specify that you want the first element of the array, Python will give an error. By sticking this int in here, we thus ensure that Python converts the number that is returned from the function called Bernoulli into an integer so that it can be used to reference a particular element of the array. To summarize, we have learned to write code to calculate histograms and to thus estimate the probability mass functions that are sampled in our experiments. On the previous slide, I showed how to do this for a Bernoulli random variable. As you can see here, however, you can use the same code for any of the discrete random variables that we have studied in this course. You just need to ensure that the arrays you create on the first line to hold what will be plotted on the x and y axis of your graph are large enough to deal with the full set of values that the random variable can take. If the random variable can take an infinite number of values, you just use a reasonably large number for n opts here, safe in the knowledge that the experiment is unlikely to return numbers that are larger than some large quantity. Within your code, you then generate a series of samples from your random variable by writing a loop to generate multiple random variables. Within this loop, you call a function that generates these random variables. The function in this case is called discrete_rv. This is all standard stuff by now that you have done many times before. What is different is that within the loop, instead of storing all the random variables for plotting, or instead of adding them all together to calculate a sample mean, as you've done in previous codes, you count how often each of the possible outcomes of the experiment is observed. This counting is done using a line like this one shown here. Once all the variables are generated, you then normalize your estimate of the probability mass function by dividing each element of the array that was used to count how often each result comes up by the number of random variables that were generated. By doing so, you ensure that the sum of all the elements of the array xvals is equal to 1. You can thus draw a graph of the outcome versus the estimate of the probability of getting that particular result, as is shown in this line. The net effect is that you have a plot of an estimate for a probability mass function for the random variable. Hopefully, that is reasonably clear. You will have multiple opportunities to try to write this algorithm for yourself in the exercises that follow, so by the end of the week, you should definitely be able to do this. Good luck.